completely gets eliminated, or it collapses, and the carriers are able to flow into the other region and constitute the current in the external circuit. Okay, so a large current flows, as you can see very clearly here, that large number of electrons are crossing into the p type, large number of holes are crossing into the n type, and so we have a large current flow. So in some sense, we say that the forward biasing will actually make the junction conduct. Now, since this is a very large current, please remember that we require, in the actual working, we require a limiting resistor in series with the PN junction. Otherwise, this current will be very, very large. It is as good as you are actually connecting, some kind of a short circuit here. Okay, so very large current may flow in this particular direction. So we come to the very first semiconductor device, and that is called as the PN junction diode. This is nothing but the PN junction that we have seen, except for when we have some external connections called as the leads. So these will be called as the leads. For external connection, these are simple conductors. And we have the schematic symbol of the diode. Please look at the symbol very carefully. Okay, so this is the direction of the current flow. So you can see here that there is some sort of an arrow here. Okay, so this actually indicates the current flow direction. Okay, this indicates the cathode. So this line over here indicates cathode, which is nothing but the N-type material, and the anode, which is the P-type material. So current flows from P-type to N-type. Please remember this carefully. Okay. Interesting thing to note again is that why it is called as diode, because it has got two terminals, first of all. Okay, and this terminology has carried over from previous generation of electronic devices, which were built specifically with what is called as the vacuum tubes. Okay, so that was the vacuum tubes, and the people had diodes in vacuum tubes also as vacuum tubes technology, and so the name simply has followed from that. Okay, in fact, vacuum tubes, in contrast to vacuum tubes, all the semiconductor devices are called as solid state devices. So they are called as solid state devices, as in contrast with the vacuum tubes, where there used to be a bulb like device, and it was supposed to be heated, and electrons were to be generated, and then they were attracted towards the positive plate, and so on and so forth. So it was a different mechanism altogether. This is a different mechanism, and this is what revolutionized the electronic industry completely. All right, so we have the anode, we have the cathode. This is the schematic symbol. Always draw the schematic symbols properly. Let us have a look at the VI characteristics of the diode. I'm going to show you a very interesting thing today. So just hold on for that. All right. So whenever I said we start with an ideal device, with a device, any device as a matter of fact, we first try to find out or try to plot its VI characteristics, the voltage and the current characteristics. So here we are looking at the VI characteristics of the diode. Okay. Now an ideal diode, voltage ampere, that is the VI curve, shows zero forward voltage. Now please remember that we are forward biasing this in this direction, reverse biasing in this direction. So an ideal diode, we can have an idealized model of the diode, and since it conducts only in one direction, I can say that as soon as the voltage forward bias is slightly more than zero, then you have the current conduction possible. Whereas when it is the reverse bias, there is no current conduction possible. This is the current axis, this is the voltage axis. So in ideal diode, it acts as a switch, literally as a switch, which is controlled by the voltage across it. Okay, so when we apply forward voltage, the switch is on. If we apply reverse voltage, the switch is simply off. Okay, so this is how you can visualize the concept of an ideal diode. But and why ideal diode? Because it has got no leakage current. As you can see here, that there is no current flow at all when it is reverse biased, and there is no forward voltage drop. So there is no, for an ideal diode, probably let us assume hypothetically that there is no barrier potential required to be overcome by the forward voltage, and so it immediately starts conducting as soon as the voltage becomes slightly positive, or even at zero itself it can start conducting. Okay, but an ideal diode does not exist. So we have the actual or the real diode, and this real diode has got some forward voltage drop. Okay, and this is what the forward voltage drop actually is seen like that. Okay, so this is the forward characteristics. So when I forward bias the diode and plot the characteristics, they are the forward characteristics of the diode, forward biased characteristics of the diode. In a similar way, I can have an reverse characteristics over here. As you can see, the reverse characteristics looks like this. And what happens here? So there is no current, or let us say there is very, very small current. This current is nothing but because of the leakage. This is nothing but the leakage current. It is the minority current. Okay. And as you can see here, as I go on increasing the reverse bias to a very large extent, maybe hundreds of volts, suddenly the diode starts conducting. Okay. This actually is called as a breakdown voltage. So voltage at which it starts suddenly, it behaves as if it is forward biased, but in the reverse direction. Why this is going to happen, we are going to see in a couple of minutes. Okay, so for a practical diode, real diode, you have a forward voltage drop. So that is, what is this drop? Basically, it is nothing but the voltage that is required to overcome the potential barrier so that the device can start conducting. Okay, so this is also called as forward turn on voltage many times. Okay, or in physics literature, it is called as V gamma, or the cut in voltage. Okay, so we are going to see in more details. So V gamma is called as the cut in voltage. Normally it is 0.65.
So,
Yes, yes.
so what is that scale change in the
Acha, very
previous
good, very
slide?
good question. I was actually going to come back to it later on. See, the scale changes because this voltage is very large. Okay, hundreds of volts. So if I want to accommodate all this into one scale, it will not be possible, isn't it? So if this represents 0.6 volts, this
Okay.
cannot represent 100 volts, no?
Yes, yes, sir.
So I have to change the scale there so that I
Oh,
can
okay.
accommodate this part of the curve too.
Okay, sir.
All right.
Got it.
Okay. So let us inspect the forward characteristics in a little bit more detail. V gamma is called as the cut-in voltage, that is nearly 0.6 to 0.65 volts for a silicon diode. Okay. We are concentrating only on silicon. We are not going to say anything about germanium diode. For your information, the germanium diode will have 0.3 volts as the cut-in voltage. But over here it is 0.65 volts. Let us say this V gamma is 0.65 volts. It is a point where external voltage actually completely collapses the barrier potential. So up to here, the forward bias, even if it is positive, it is up to 0.65 volts, for example. In spite of that, current will not flow unless and until the external voltage crosses this cut-in voltage. This is very, very important. Once it crosses this voltage, as you can see, there is a sharp increase in the current flowing through the diode. Okay. So the current starts flowing after the cut-in voltage is achieved. Now there is something called as, see, this is VI characteristic. So naturally, we can, as a slope, we can find out the slope is nothing but the resistance of the diode. So we normally call it as the bulk resistance. And the bulk resistance, please note this formula carefully. You may require it very often in later courses. So what is this bulk resistance? For example, if my current flow at this instant is I1, correspondingly, if I project it here, the voltage drop across the diode is V1. Okay. So if I want to find out the bulk resistance, which is mostly to be calculated, not given in the datasheet directly, is the formula is this. How can you find out? It is simply Y2 minus Y1 divided by X2 minus X1. The other way around, because it is IV characteristics rather than VI. Okay. So V1 minus V gamma okay, divided by I1 minus 0. Why 0? Why is this 0?
So because before the
Yeah,
V gamma
because at
no
this
current
point the
is
current is 0. The current is 0 at this point, okay? Fine. So that is called as the bulk resistance of the diode. Now the equation that governs the forward characteristics or equation, we can plot we can make an equation of this, and this equation is given. This is a very important equation. What does it say? Forward current is equal to Is. We are going to see why this. What is this Is? It is actually nothing but the leakage current, also called as the reverse saturation current. Is also called as reverse saturation current, into e to the power Vd by eta Vt minus 1, so many amperes. So I can easily find out this is the nature of this curve. As you can see, it is not linear. So diode is a non-linear device. If you compare it with the resistor, resistor is a linear device, whereas diode is a non-linear device. Okay. All right. So this is basically the equation which governs the forward characteristics. All right. Now let us break this down and see each of the items properly. Vt, what is this Vt? Vt is equal to K into T by Q, so many volts. It is actually called as the voltage equivalent of temperature. Now this demands some explanation. If you look at this equation, we already saw that temperature is going to affect, isn't it? The temperature is going to affect the curve. The temperature is going to affect the current of the PN junction diode. We saw that yesterday. All right. Why was that?
Yes, sir. Yes, sir.
Yeah, because temperature is going to impart some extra energy to the electrons, and then naturally the current changes over there. All right. Now you can see here clearly that it is as good as I am applying some current. So it is voltage equivalent of temperature, as if instead of just replace the temperature by voltage, I'm going to get a similar effect. What happens to the temperature? What happens in case of increase in the temperature? Increase in the temperature will lead to higher energy, and we have already said that the semiconductor has got negative temperature coefficient. Means what? As temperature increases, the resistivity decreases. Correct. So as if I am applying an external voltage instead of temperature, I am applying external voltage. The effect is going to be same, no? Whether you decrease the resistivity by temperature or you decrease the resistivity by an external voltage. Okay, I can have a similarity here. So this temperature is nothing but, I mean, this particular voltage equivalent of temperature is nothing but as if I am applying some voltage equal to Vt, and then the effect that is going to be there is reflected in this particular equation. So please remember this equation, this particular term, voltage equivalent of temperature. It is very important, one of the most important concepts. And how is it made up of? It is made up of K into T by Q, where K is the Boltzmann constant, Q is the electronic charge, and eta, we are going to see about eta later on. Okay, T is absolute temperature. So K into T by Q. So this is constant, this is constant. So this Vt is going to change only with temperature. Remember, this temperature is in Kelvin. All right. Okay, so this part is done. Voltage equivalent of temperature. Now let us look at the other parts. Vd is the diode terminal voltage. That is the voltage that you are applying across the junction. Is is the reverse saturation current. We'll talk about it in more details in the next slide. Okay, so I can find out, given the amount of voltage, given the amount of temperature, ambient temperature. We have to be very careful about this because this ambient temperature plays an important part. Okay, so Vd, given Is is also a constant quantity. So given Vd, given Is and Vt, which is a constant for particular temperature, I can find out what is the current flowing through the diode. All right. So this equation is very, very important. Okay? All right, guys, are you
Okay,
following?
sir.
Yes, sir.
Okay, sir.
Okay,
Yes, sir.
fine.
Yes,
So,
sir.
so we see that the forward characteristics is modeled by this mathematical equation. Let us see, come back to this effect of temperature in forward characteristics. Now, as you can see, Vt is, I can, K and Q are constant, so I can write it as T divided by 11,600. And for a room temperature of 27 degrees Celsius, that is 300 Kelvin, this Vt works out nearly to be 26 millivolts. So if temperature is not given, or it is said that temperature, room temperature means 27 degrees Celsius, and you can safely assume that Vt is always 26 millivolts. So as if you are applying 26 millivolts over there. Okay. And since Vt appears in the diode equation, T does affect the characteristics. You can see here the change in the voltage across the diode. Actually, this is the d by dt of Vt. That is the rate at which Vd changes with temperature is worked out to be nearly minus 1.8 millivolts per degree Celsius. So as you can see, as temperature increases in this direction, okay, the voltage across the diode reduces. So if temperature increases, Vd reduces by how much? Minus 1.8 millivolts per. So you can nearly say that this is nearly equal to 2 millivolts per degree Celsius. Just to remember it. So remember that voltage across the diode will reduce if temperature is increased. In this case, okay. So as you can see, this is again a very important consideration. Many times you're going to use this kind of relation. Have you understood this? So these are a separate set of curves. One was when the ambient temperature was minus 50 degrees. One was when it was 25 degrees, and the other one it was 100 degrees Celsius. So as you can see that Vt actually decreases. Or in other words, I can also say that if I have the current constant over here, if I keep the constant, if I keep a current constant over here, and if I draw a straight line here and project it all the way down, you can see that the voltage across the device actually reduces with increase in temperature. All right, so this is one of the reasons why temperature is a very important factor that has to be considered when we use semiconductor devices. All right.
Yes, sir.
Oh, okay.
Yes, sir.
Let us inspect the reverse characteristics in details. The reverse breakdown point is also referred to as the avalanche voltage. As I was saying, that if you increase the reverse bias across the junction to a very large value, there will be a breakdown. Now, what is this breakdown? It is called as an avalanche effect. Why it is called as avalanche? Or why does it occur? That is, it occurs when the carriers accelerate and gain enough energy to collide with valence electrons and knock them loose. So in fact, if you just go back to the the previous diagram where we had electrons over here, and now we can see that given large voltage difference, okay, if I have in a particular space, if this particular distance okay, if this distance is too small, then a small amount of voltage applied, okay, what is the field, that is electric field that is going to be generated is this distance d. I am applying voltage B, so it is V divided by D, so many volts per meter. Okay, this is the field, electric field that is generated. Now, as you can see, the junctions are very, very small. The distance is going to be very, very small. Let us say, for example, the distance is about 1 micrometer. And even if a small voltage of, let us say, 1 volt is applied, what will be the electric field intensity? This is called as intensity. So intensity will be 1 mega volt per meter, huge value. Okay, so as I go on increasing the reverse bias, these electrons which are actually bound in the covalent bonds, they get detached because of this very large voltage differential, okay, or the intensity, and they accelerate. Okay, and they accelerate, and in the neighboring atoms also they will try to dislocate the atom. So I can have 2 electrons, then 2 electrons will give rise to 4 more electrons. So a large number of, very soon, a very large number of free carriers are available. All right, and that is why we have a very large current flowing in the reverse direction, and this point is called as B breakdown. In fact, this is a dangerous situation. Why? Because it most likely will destroy the junction. So this breakdown should never be arrived at. You should never apply a large voltage enough, even nearby to breakdown. Now this actually, as I said, causes the avalanche of carriers, and the reverse current flows very fast, increases tremendously. So the minority carrier current flows and is called as the, whereas wherever in this particular region it is safe enough, and we say that the leakage current flows in this particular region, which is called as the reverse saturation current. Again, from diode current equation, if Vd is negative, okay, the magnitude, in magnitude, the exponential term becomes negligibly small compared to the unity, and the diode current becomes equal to this. So if you remember our diode equation, now since it is, the direction is reverse, instead of calling IF, I'm going to call it as IR, which is equal to IS into e to the power Vd. Now Vd is negative. Why? Because it is the reverse, in the reverse direction, eta Vt. Now eta is an intrinsic parameter. I just forgot to tell you about this. So it's an empirical constant, 1 for germanium, 2 for silicon, but most of the times it is ignored. So this we can ignore, -1. So if Vd is negative, I can say that this is nearly equal to Is into this entire thing reduces. Okay, so it is nothing but 1 to the power 1 divided by e to the power Vd by Vt, which is this quantity. If V is sufficiently large, this quantity will diminish to very small quantity, tends to 0. So I can neglect this term here, and then it becomes equal to -1. So IR is equal to -Is, or in simple plain words, my reverse leakage current is the current which flows when we have the reverse characteristics. So we have to be careful about this also. Let us see why. Because temperature also has an effect on this reverse saturation current. How does it affect? We'll see. So you can see here that Is is temperature dependent. Why is it temperature dependent? Concepts. Refer back. Why is reverse saturation current dependent on temperature?
जितना टेम्परेचर बढ़ेगा सर, उतना ज़्यादा उसकी रेजिस्टिविटी कम होती जाएगी ना सर. तो जितनी रेजिस्टिविटी कम होती जाएगी सर, उतना ज़्यादा रिवर्स
Let me put it this way. As temperature increases, the minority carriers are created, isn't it? As temperature increases, minority carriers are created. We have already seen why this happens.
Yes, sir.
All right. So minority carrier, if they become, if the number increases, naturally we expect that the minority carrier current also increases. That is it. So as temperature increases, number of more carriers are generated, but of course they are in minority, and the current also increases. It is seen that Is doubles for every 10 degrees Celsius rise in temperature. Of course, the value of Is is very, very small. It can go up to -14 to 10 to the power -15 amperes. So this is very, very small current. Modern diodes have very small leakage current. So this is in picoamperes. I'm just taking it for example. So for a lower temperature, say T0, this was the curve. If I increase the temperature and again plot the characteristic, it will be seen over here. It has doubled. Again, if T2, so this should be, the difference should be 10 degrees Celsius. Here the difference is 10 degrees Celsius. So it doubles for every 10 degrees Celsius rise in temperature. This is also a very important concept. The equation that we can use is Is at T1 divided by Is at T0 or T0 is equal to 2 to the power T1 minus T0 by 10. Or if I want to find out the reverse saturation current at the new temperature Is at T1, it simply is Is, which is at T0 into 2 to the power T1 minus T0 divided by 10. Okay, this equation helps us in estimating, finding out what will be the new reverse saturation current if I increase the temperature. All right. Okay. Now, looking at the characteristics, how do I plot the characteristics using the simulation software? I have not specifically mentioned any software, but the screenshot necessarily are of Multisim. So if you want to really plot these characteristics, what you can do is you can simply connect a current source like this, and of course this is only for the purpose of plotting the characteristics, and you can see the characteristics is a little bit rotated. We will not be in a position to get what we saw in this particular fashion, right? This particular fashion, but at the same time it is rotated. Doesn't matter. We are able to see the cut-in voltage. Again, this is some flaw with the. There is a bug in Multisim which does not let me. In fact, this is the current. So this value is supposed to be the current in amperes. Okay, so this is the IV characteristics. As you can see here, you can plot very nice characteristics using this circuit which I have shown over here. This PR1 is the voltage probe, and you can use what is called as the DC sweep. We'll have one session on Multisim if you want. We can have a session on Multisim, how to start using it. All right, because you're going to perform all your practicals using Multisim or microcap, whatever is available. All right. Okay, so these are the characteristics which you can plot using Multisim. Now let us have a look at diode as a circuit component. As I said, we require to have series resistance to limit the forward current through the diode. Otherwise, it will become a very large current. So this is, again, as I said, this is a circuit component. Now diode to be used as a circuit component. Please remember, since this is P type, this is N region or anode and cathode, this diode will be forward biased. Okay, why? Because this is positive, this is negative. All right. Now this forms a loop. There will be some current flowing through here, which I will call as I. Okay, let us not give it any designation. So this is I, current is I. Can I write an equation using KVL for this? Let us write down the equation. V1 minus I into R1 minus the drop across this is going to be plus minus. This we call as VD or VD1 equal to 0. So if I want to find out the value of current, what should I do? I is equal to what? So call this equation 1. I is equal to V1 minus VD1 divided by R1. This is how I will try to find out the current flowing through the diode. All right. Is this okay? Guys?
Yes, sir. Sir?
Yes.
Excuse me, sir. Sir, that VD1 is dependent on the material of the diode. Like it is germanium, it is 0.3, or silicon, it is 0.7.
Okay, yeah. So
is it that like that?
of course. I'm not at all getting saying that. As I said, cut-in voltage. When I described cut-in voltage, I said that for germanium it was 0.3 and for silicon it is 0.65. That is nothing but the forward voltage drop.
Okay, sir.
All right. Normally, germanium is totally, it's not at all used. It is totally discarded. So it is. I don't want to unnecessarily confuse you with different device, different material altogether. So I'm avoiding the mention of germanium altogether. Okay.
Okay, sir.
All right. So going back to this. So is this equation clear? I'm simply using KVL.
Yes, sir.
That is the reason why we started with the basic concepts using these laws and theorems, right? Okay, but at the same time, okay, let me switch to a different application. Okay, we can do it here also. So please remember this equation. Meanwhile, I switch to a different application, specifically one note I'll be using. Okay, now are you able to see this OneNote page here?
Yes, sir.
Right? Is this okay? So let us write
Yes,
down
sir.
the equation once again. What was the equation? It was V1 minus I into R1 minus VD. We'll call it as VD only, equal to 0. That translates to I1, or sorry, I is equal to V1 minus VD divided by R1. I can manipulate this again. So I is equal to minus 1 by R1 into VD, yes, plus what? What do we have?
V1 by R1.
V1.
Yes, so it will be again V1 by R1.
R1.
Doesn't it look like Y is mx plus c? All right, where m is minus 1 by R1. So if I plot this characteristic somehow, if I plot this IV, let us say this is I, this is V. So what is the, here in this case, this is Y, this is X. So how will it look like? The intercept is V1 by R1. So somewhere here, which is a current. V1 by R1 is nothing but the current. So you have some intercept here. The slope is negative and is dependent on R1. So you expect a line like this. All the way over here. Is this clear? So this will be what? V1 by R1, isn't it? The slope is -1 by R1. ठीक है? Very important thing, huh? Please be careful about this. ठीक है, everyone?
Yes, sir.
Yes, sir.
Yes, any doubts, any questions?
So V1 by R1.
ये क्या है? V1 by R1. C.
Okay, sir.
Y intercept.
Yeah, sir. Got it, sir.
Got it, no? Yeah, it is very easy. All right. Now at the same time, I'm having an equation for the diode current, which is Is e to the power Vd by eta Vt minus 1. So if I go back to the circuit diagram, let me redraw it here. Something is happening here. Okay. So if I go back to the circuit diagram, I'm having this voltage here as V1, resistor R1. You have the diode D1, and you have the circuit completed and the current. But we have to respect this also, no? So this current has to be same as the current that is this. So this current and this current are one and the same. Agreed? Yes or no?
Yes, sir.
They're
Yes,
one
sir.
and the same. They're one and the same.
Yes, sir.
So I'm having corresponding to this, I'm having, what am I having? I'm having a characteristic, forward characteristic of the diode. I'm having like this. Isn't it? Agreed? Yes or no?
Yes, sir.
Okay.
Yes, sir.
And
Yes, sir.
you can see that these are two equations. This is one equation and this is another equation. So you have two equations, two unknowns. So a line, actually it is as if a line is cutting this particular exponential curve at only one point, and that point is, it will have same coordinate. So the solution to this, solution to both these equations is a point over here. Agreed? Yes or no?
Yes,
Very
sir.
easy.
Yes, sir.
Yes,
Nothing to worry about. If you have got any
Yes,
problems,
sir.
you can ask me immediately. So what do we have here? So we have two equations, one equation corresponding to the diode and one is the loop equation, and it will be possible to have only a one value of I where both these curves, one of the curves and the lines, they intersect, and this point we normally call as the Q point. Q. Oh, the other way around.